Okay, so next we'll have a presentation from Chenn Zhou at Purdue Northwest. She is not able to join us in person, so we've asked her to give her presentation virtually. And I believe we need to give it another moment. Oh, we are ready to go. Great. I do also want to remind everyone that we have a poster session available all day with the poster authors and refreshments available from 1:30 to 2:30. And that's upstairs at Stewart 214 A and B. And also, please join us at the conclusion of the summit today at a reception at the Purdue Union East Terrace from 4:15 to 5:30. And the East Terrace is accessible from the basement level of the Union and is located where Pappy's Sweet Shop used to be. And also, if you didn't know, restrooms are in the Hissey Library, which is just over there, and also on the second floor. Okay. So, Dr. Chenn Zhou received her PhD in mechanical engineering from Carnegie Mellon University and joined Purdue Northwest after 3 years of industrial experience. Dr. Zhou now has 40 years of experience in the areas of computational fluid dynamics, energy, and air pollution control. She is on the cutting edge in the integration of advanced computer simulation and visualization for solving industrial problems. She established the Center for Innovation through Visualization and Simulation, CIVS, in 2009, and the Steel Manufacturing Simulation and Visualization Consortium, SMSVC, in 2016. Dr. Zhou has conducted many funded research projects and collaborated with over 170 organizations, which have generated significant educational and economic impacts. She has published over 450 technical papers and abstracts and 5 copyrighted CFD codes. Dr. Zhou has received numerous awards and has been AIME Honorary Member, ASME Fellow, as well as AIST Distinguished Member and Fellow. So today, she will talk about industry application of multi-physics, computational simulation, and visualization. Hello, Dr. Chenn, can you hear me okay? Okay. You're still on mute?
Thank you so much.
Okay.
Can you hear me now?
Yes, I can. Thank you.
Hello? Can you hear me? Thank you. I'm very honored and very excited to be here, talk about our research using advanced computing. So in my talk, I will start with some background information and followed by methodology and examples. And so I'm located in Hammond, Indiana, and which is surrounded by industry. So that's why our research is really focused on how to utilize the advanced computing to help solve industrial problems. So let me start with introduction. So we all know we're in the exciting time for Industry 4.0. We also call this as advanced manufacture or smart manufacture, or some people even call digital transformation. So basically, also people call this as the fourth industrial revolution. So in this, Industry 4.0, what is important is those, and of course, simulation. So getting more important because when you apply that
We're going to check and see if she can rejoin.
Hello, sorry, looks like we have some technical problem.
Welcome back.
I got a backup plan, so that's good thing. So one thing didn't work, and so the second thing should work, okay? So let's get started again. Okay, so can you hear me well now?
Yes.
Now.
Yes, everything is good. Thank you.
So I think you heard this part for the how the simulation visualization play important role for Industry 4.0. So then so in 2009 we formed the Center for Innovation through Visualization and Simulation, and to focus on applied research and to integrate the simulation and visualization together. So we have been working with more than 160 organizations, more than 460 projects. But then in 2006, still industry got together, they wanted to have a specific consortium to develop and apply simulation and visualization technology to improve the steel industry competitiveness. So currently we have 15 industry companies and focus on 8 research areas. And from those areas, we actually pick up specific projects. So I'm going to show some of those projects. So one thing I want to emphasize now is about 5 years ago, the digitalization become very important. So that's exactly what we're doing. So we're focused a lot on the physics-based and data-driven. But then in the last 3 years, decarbonization is becoming more and more important. So our new focus for the both center and the consortium are on the digitalization and decarbonization. So give you a little more idea about the simulation. What we do basically is computational fluid dynamics. And when we use the advanced visualization, you see this figure, you're actually inside the blast furnace, the video shows. And those inside the blast furnace, you can look at the data generated by computational fluid dynamics. You can look at the CO2 emission, temperature is like a software sensor. So by coupling this simulation with visualization together, it provides great advantage for the insight, foresight, and the efficiency. So basically, CFD give you a physics-based data, and visualization can help people understand, easily communicate, and greatly enhance the value of CFD. Now, let's talk a little bit more on CFD because this is a high fidelity, computing, and it needs a lot of computing power, but also a lot of effort. So I just basically summarized to a few steps. When you solve a problem in industry, you need to start with geometry, and nowadays it's much easier now with the AutoCAD and everything. But then you need to make a mesh. You need to have boundary condition because you're solving non-linear partial differential equation. You need boundary conditions, and those boundary conditions need to be from industry. Then after that, you need to convert those partial differential equation into algebra equation through iteration. After you get the results, we visualize and we need to validate because validation is the key. Otherwise, it's easily provided. People say garbage in, garbage out. So once the results are validated, you can run many, many what if to optimize the performance of the process. So that's basically for every project, we need to go through those steps. Now, as I say, when we integrate simulation with visualization together, it's greatly enhance the value. Now, furthermore, when we put the CFD and visualization, but also sensor data and reduce the auto model, machine learning all together, actually we can really make a very efficient, effective, and economical tool for real-time visualization, very quick offline modeling, and quick decision making, and also high fidelity analysis. So this way you can test out, for example, hydrogen injection, or electrification, and also the whole virtual furnace could be used for virtual training. So, you probably know this quote a lot. Without data, you're just another person with an opinion. Now, I want to say with computing, simulation, we actually provide the physics. So it's true, without physics, you're just another person with opinion, right? Or data. So by doing this way, we really focus on provide a physics-based, data-driven decision to answer many what-if questions, and you can reduce the risk and shorten the cycle for develop new transformative technologies. And you can provide the real-time monitoring, control, and more effective training. So I'm going to start giving you some examples. Before that, I want to emphasize again the application and impact. So for the application-wise, I always tell people, your imagination is the only limitation. Specifically for industrial application, we have been used this kind of technology to help industry to do design, troubleshooting, optimization, scale up new process operation, maintenance, safety, and the training. And specific impacts are very important: decarbonization, energy efficiency, and so you can list the many impacts. First example is our signature project for blast furnace. We started this research about 20 years ago for the only for CFD simulation, computational fluid dynamics. At that time, the visualization technology is not advanced yet. So we actually developed very comprehensive multi-physics, multi-species reactive models. We divided by whole furnace into 3 parts because if you want to do whole furnace, computing time, even with high quantum computing, would be very long. So we find the so-called sectional approach, and we do section by section, and basically we divide by 3 sections. From bottom, we call hose, then middle is raceway, top we call shaft. Each section can work standalone, but also coupling together. Especially now, we want to try hydrogen injection and the electrification for the plasma injection, for example, for decarbonization. So this kind of model very important to very helpful. So since 2002, and we have also combined this now with visualization and develop virtual blast furnace. Actually, we have industry partner, told us, save the cost significantly and the downtime reduction. As you see here, one of them, industry furnace, saved $8.5 million per year and reduced downtime by 50%. That is very significant. So, and now we're using this model developed, along all those 20 years. We continue to improve and also make advancement. So those are some examples, the recent examples. So we help the Cleveland Cliffs to design and implement the injection of coal with natural gas. Before this, emphasize on decarbonization, people already use the coal and the natural gas replace coke, because coke is not just expensive, but very toxic for environmental. And so now, few years ago, we helped design those how to inject the coal and natural gas, actually increase the coal combustion efficiency by 25%, and the solution was implemented. Then we also did for trying to help, carry the coal into the furnace using natural gas. Normally use nitrogen. So again, by doing CFD, we help the many scenarios and find the optimum solution. And that one is in the implementation, and it can increase the productivity by 2.5%. And also, meantime, we actually solved one of the issue. For example, this figure is clear, okay? So to inject the coal and natural gas and get burned all the time, they could fail. So we actually find out what is wrong and why it is wrong, how to fix that. So these are really practical application. Now, with decarbonization emphasis, we already used the model to test out the hydrogen injection, and we found out in the blast furnace, and you need to be very careful where to inject, how to inject the hydrogen, how much, because hydrogen injection is different chemistry, compared to natural gas, coal, and coke. So they can actually cause some instability because the quenching effects, the hydrogen components that can actually react with iron ore, because blast furnace basically is convert iron ore into liquid iron. So that kind of additional reaction can suck in the heat and cool down the furnace and may cause, shut down the furnace. So we actually had a quantitative evaluation, how much hydrogen you can inject to keep the stable for specific furnace, and also give you what's the reduction of CO2. For example, in one of the furnace, we found that if you add 15 kilogram hydrogen injection, you can reduce 5.5% CO2. So, so this actually research is still ongoing, and so let me move to another example, the reheating furnace. So blast furnace is the beginning of integrated furnace to use iron ore to make liquid iron. Then you further down to the steel making, and you make a liquid steel. After that, you need that's they call rolling mills. You need to have the steel plates heat up to the further rolling. So what you see this movie is actually inside a reheating furnace. And so the common issue is energy efficiency and the uniformity of temperature distribution. So by doing the CFD simulation plus visualization, actually what you see here is a real furnace. We actually even connected with sensor data to almost real-time monitoring. And one of the big issues for this furnace is also they have requests on the different grades of the steel. Each time, if the grades are different, then you have to change the operating condition. So with these two, actually, we help the industry to do real-time monitor and operation guidance on this. So again, currently, one of the bigger hot topics is hydrogen injection. So again, we, test out hydrogen injection into reheating furnace because again, chemistry is different when you do hydrogen injection compared to normally natural gas injection. So your heating rate is different. So the question is, how much hydrogen, we needed to do to replace natural gas, but keep the same heat flux. How that affected the temperature inside furnace and also the slab. How that impacted the uniformity of the temperature and the steel quality. So because time I cannot give you too much details, but basically, again, we have been used this CFD simulation, investigated multiple scenarios. This is the one example is we found out the 16% higher temperature in general for the hydrogen injection if you keep the same amount, but all otherwise, actually, if you want to keep the same heat flux, you can use less hydrogen. And of course, CO2 reduction is, if you use totally hydrogen, you don't have CO2, right? However, there's always some challenge. So if you have hydrogen injection, you reduce CO2, but you generate water, H2O.
So if there's too much, you have to find a way to remove that. Because otherwise, you have compensation issue and other issues. So again, CFD simulation can give you a very detailed quantitative analysis. Now, also, when you do hydrogen, all other ways to reduce CO2, and if temperature is higher, you may cause other emissions, like for example, nitrogen oxide. That's also air pollution. So you cannot just say, I only look at CO2 reduction. You also need to look at other emissions. So this model have been developed also more than 15 years ago. We're using this to evaluate every details on flow properties and also emission inside the furnace and also in the exhaust place. So let me move on. This is another practical example actually already implemented, but I cannot tell you exactly what company and also what is the process because confidential information, but I can tell you this is the boiler, and this boiler fired multiple fuels, different compositions. So the company wants to mix hydrogen, okay, for decarbonization purpose, and together with other fuels. And so how much can we put in? Again, you need to know how that, affect the process. So we actually tried many different cases, and you can see here standard operation without hydrogen and with additional hydrogen, and obviously temperature is higher. So they want to make sure there's no issues on the overheating the boiler wall, because if temperature is higher, the boiler need to cool down, and if otherwise that's fail again, you get hot spots. So we're able to identify how much fuel of hydrogen can add in without overheating the boiler walls. And we gave the range of the operating condition, and company already installed it, follow the guideline, and it works very well. So another example, again, people want to try hydrogen by all means, right, to replace natural gas in any possible combustion process. So this is another example, gas turbine combustion. And so we tried, you can see here is some very preliminary results, but very promising. So if you have 100% natural gas, so this we call baseline CO2 emission. You add 25% of hydrogen, okay? You can see the color. The red color means higher CO2. And so then you see the CO2 emission is less. Then if you add 50%, this trend shows very good qualitatively, but our simulation can give you quantitative analysis on this. And so you also, again, not just look at the CO2 emission, temperature distribution, you want to make sure there's no thermal damage on combustion walls. So let me move on. So electric arc furnace is a big way to reduce CO2 for steel industry. And right now in the United States, we're ahead for other countries. So there's 70% electric arc furnace, okay, in the whole steel industry now. Another 30% is blast furnace related. EF is great for CO2 reduction, but of course there's some limitation. You cannot use 100%. However, you want still make sure optimize electric arc furnace operation. So it's very complicated like a blast furnace. So we use the same approach like blast furnace, divide the whole process, multi-physics, thing into section, but this time it's by operation. So the operation-wise is this: an electric arc furnace uses the arc to heat up material. In this case, you put mostly scraps. So you preheating the scrap, then you melt, solid become liquid, and then you do more refining to make sure the quality of the steel. So we divide again into multiple models. Then each one catch up the major physics and chemistry, then integrate them together. Again, each one can be working standalone, but coupled together. So this has been now a state of art. Once we started this modeling 6 years ago, there's no such comprehensive model, CFD model in the world. Now industry people evaluate this and think this is now really on the cutting edge, like our blast furnace model. So we basically developed validate the model, directly work with industry, and so each model can be used to simulate the different stages. So I'm not giving you the details, but I'm going to show you some example here. And this is a practical example. One of the company, CIVS, they have an issue. Again, when you're dealing with high temperature process, you need to always make sure there's not an overheating, right? And damage the equipment. So they found there's overheating issue on the wall of electric arc furnace. So why? How to solve that? And that's, it's very challenging. So with our model we developed, so we actually did the simulation for the whole electric arc furnace. This wall heat up is not just temperature issue, it's related to the whole operation. What we found out is this: when you have this electric arc, basically they pull electric arc down into the solid, okay, they call scrap. And so how much you put in will directly relate to the heat generated. And that heat will go, of course, propagate into the whole system. So what we found out, this arc, okay, how much immersive into the liquid or solid will directly affect the wall temperature. And so our quantitative analysis showed if arc power increases, and of course, then your arc, will provide more heat, will overheating. So we actually find out the operating window. If it's larger than 85.1 megawatts, and you will have overheating, okay? But you want it is not the less the better. You want to also maximize the heat absorption. So therefore, there's also lower limit. You want to make sure operate above 59. So then industry validate this and implement it. And so what the industry want is they want to make sure we have an online calculator, web-based. So we did many simulation and make it as an interface. And so then, so the operator or engineer can just put the operating condition and look at this condition will have overheating or not. So in this case, you see the overheating issue, they give you a warning. Then you change another condition, you see, okay, we're safe. So this gives you a very user-friendly tool, of course, and this has been pre-calculated many cases. So that's a trend of what the industry wants. They just because they want to really apply to operation. So they always want us to develop some online calculator, or in the blast furnace case, not only do online, we actually want to use machine learning to do a lot of reducible model based on CFD simulation. So let me move on. So I talk about the steel industry, but our center work, actually with multiple industries. And this is a local company called Dwyer. They make flow meters. And so they're worldwide, very famous on the flow measurements. So they had a challenge. They developed a new type of the measurement, okay? So it's using those electrodes to calculate the fluid velocity. So this is their facility here. You want to see here, there's one of my staff there. And then you put this flow measurement device inside, and they can calibrate, okay, the flow meter. But what they found out that this calibration is very unstable, very time consuming, not even accurate enough, and they don't know why. So we actually use the very high fidelity, the high order turbulence model to calculate, to find out what's going on. And you need to go to very small area near the tip here. And so, in fact, what happened is those turbulent vortexes, and the vortex could be also unstable, can be easily, cause the unstable and also inaccuracy. So we run many cases, and actually also first find out what is wrong, then evaluate the different scenarios and many different design. So finally identified, what is the optimum design. As you see here, this figure before, you see that this flow distribution is different. And after optimized design, the flow field changed. And they give very stable calibration according to the industry. So they actually implement this new design and save the calibration time more than 50%. That's a lot of cost saving, okay? And so that's very, actually very fundamental research, because we have to go through those turbulence model, very fundamental, but then apply that fundamental knowledge into industry directly and implement the solution. It's very exciting, okay? Another example, this is also very exciting example. I mentioned earlier, this kind of technology, simulation plus visualization, actually is a great tool for scale up. Department of Energy actually did a quick research. They said that most of new technology development fail at the last stage, which is commercialization stage, because if you have a process in operation, industry is very reluctant to have you try new things without sure it works. So the DOE fully recognized this advantage of this tool. So we have a project from Department of Energy Advanced Manufacturing Office to help industry. It's called the carbon tech. They actually have a new process to make iron nuggets. So the new process is basically using the biomass to replace coke. As I say, coke is expensive, toxic also. So this process they designed to produce high quality pig iron nuggets, and then of course significantly reduce CO2 emission. So they did a lot of laboratory tests, and when they doing when they did for the pilot scale, so we help them actually model the whole pilot scale real device, the whole process, and many cases is also multi-species reactive flow with certain reactions. So we validated our model with their pilot scale data, very accurate, okay, within 5% difference. Then with this confidence, we started to help them evaluate their commercial scale design. And so we did evaluate 6 different design variables and 15 different cases actually recommended final design. And in addition, because they want to go to industry to convince people this is a good process and they want to do the full scale. So we did a visualization, okay, of the whole plant in operation, not just the reactor part, the whole process, whole from beginning to the end. And so not just animation, we actually, again, included the CFD data. So this way show the details of the physics and highlight the ways how to increase production and lower the cost. And so they use that, it's interactive video, or you can just show video. They used this actually video for marketing purpose and also for convincing investors, talk to industry, and of course the simulation provided, a lot of fundamental understanding and also practical guidance for optimization and design. And so now actually, because COVID, things are slower for commercialization, but they already identified the site in Burns Harbor, Indiana, to build up a full scale. And so again, this is a great example how the simulation and visualization can be used for scale up. I got 2 minutes, so perfect timing. And to summarize, I truly believe advanced computing is key for our future, not just for steel, it's for whole advanced manufacture. And digitalization, decarbonization will be more and more important, but that's why advanced computing play extremely important role. And specifically, what do we do for simulation and visualization, combined with data, sensor, machine learning, I truly believe this would provide physics-based and data-driven and a tool to help industry for the greater future. With that, I would like to thank all the government funding agencies and all my company sponsors, all our collaborators, our consortium member companies, of course, my center faculty, staff, and students. Thank you for your attention, and that's the end of my presentation. Thank you.